Let's talk a little bit about solving the problem we already modeled. One way is that we solve it by intuitive approach. It means that based on the understanding of the problem, guess some of the variables and find the other ones. Let's say for example, in this problem, because first product gives a higher profit, I just produce all the material to product 1 and nothing for product 2. It means that x2 is 0, and then I try to find the value of the x1. So if I put x2 0, this equation becomes x1 less than 200 because x2 is 0. And the second constraint, if I put x2 0 here, I got 900. 9 times x1 less than 1566, or x1 is less than 174. And then for the third constraint, if I put x2 equal to 0, this term goes away and we have 12 times x1 less than this number, or it gives me this number. So I have 3 values for x1. x1 is less than 200, x1 is less than 174, and x1 is less than 240. Because 174 is less than all of these numbers, this number is the right number. And this number satisfies all other numbers. For example, 174 is less than 200 and 240. So x1 is 174. If I put x2 0, the maximum I can produce is from product 1 is 174, and my profit based on this production plan would be $60,900. Someone may say, okay, why not put x1 and x2 equal and solve the problem? You may try to find the solution based on this concept. I mean, you can assume x1 and x2 are equal, and then put this one equal to some small x, and solve this problem. This is left for the student as self-practice. The intuitive approach is not the only way to solve the small problems. Another way to solve the problem is the graphical approach. In the graphical approach, we plot each constraint on the graph and find the solution based on the changing the objective function. But before starting this model, we have to have some definitions. We need to define 2 terms. One is that feasible solution. The feasible solution is any solution that satisfies all constraints of the problem. Remember, in the intuitive method, the reason that we choose x1 is when x2 is 0, x1 is 174, is that this number satisfies all the constraints. So x1 equal to 174 and x2 equal to 0 is a feasible solution, because if we put these numbers in these 3 equations, it satisfies all the equation. So this solution is a feasible solution. Another feasible solution is that I can put both x1 and x2 as a 0, because it satisfies all the constraints. Another term is feasible region. The region covers all the feasible solution is called feasible region. In a bit, we explain both terms more clearly in the practical example. If we want to solve a model by the graphical approach, we have to plot all the constraints and then find the feasible region and then find the best solution. Recall the example we had already discussed and solved by the intuitive approach. Let's plot this model and solve it by the graphical approach. First of all, we have to plot x1 and x2 because we are dealing with 2 decision variables. So we draw a plot in x1 and x2. x1 is this axis and x2 is this one. And then we plot the constraints. In order to plot the constraints, we have to consider the equality constraint. That is, we need to plot x1 plus x2 equal to 200, and for the second constraint we should plot 9 times x1 plus 6 times x2 equal to 1566. And then for the third constraint we have to plot 12 times x1 plus 16 times x2 equal to 2080. For the first constraint we have x1 plus x2 equal to 0. To draw this constraint, we assume x1 is 0, and then it gives me x2 equal to 200. So this point on the graph. And the second one, I assume x2 is 0, and it gives me x1 equal to 200. That is this point. Because this constraint is a linear one, I just can connect these 2 points together, x1 and x2. This constraint is in form of less than or equal, so we have to find is this area or this area, which one is the constraint covers. For this purpose you may test 1 point and then decide. For example, you may test 1 point right here, there, and if this point is not satisfying, then the feasible area is this one. But if we put 0 and 0, that means x1 is 0, x2 is 0, 0 plus 0 is less than 200. It means this area is represented by these constraints. So x1 plus x2 less than 200 covers all this area. And recall that x1 and x2 are positive. So this is the area that shows by first constraint. And the sign variables, I mean x1 greater than 0 and x2 equal to or greater than 0. So this is the first constraint. So this is a plot of the first constraint, and then the feasible area represented by first constraint is this blue area. When we plot the constraint as an equality, we call that the boundary line of the first constraint, and this area is the feasible area represented by the first constraint. Now plot the second constraint in the equality constraint. If similar way we can present, let's say x1 is 0, and then we find the x2, which is x2 becomes 1566 divided by 6, and then x2 equal to 0, and similarly we can find x1 is 1566 over the 9, and then we plot this one. So this is the second constraint. The x1 becomes 174, the way we did in the intuitive example. We got this number, and x2 is 261. This is the first constraint, this is the second constraint. And let's say put 0, and to find which one is the feasible area. 0, 0, 9 times 0 plus 6 times 0 becomes 0, which is smaller than 1566. So this area shows the feasible area, and this one is feasible area for the first constraint and second constraint. So the combination of these two lines gives me this one as a feasible area so far. And then we have third constraint. So if we want to have the third constraint, we have to plot the boundary line, which is we have to consider in the equality. Similar to first constraint, we put x1 equal to 0 and find x2, which is 2880 divided by 16, and we put x2 equal to 0 and we find the x1, and which is this number, and then we connect these two points, and this is the third constraint. After plotting all the constraints, this becomes feasible area. This is our feasible area or feasible region. So we plot all the constraints and we find the area which is common between three constraints. Any point that we select from this area is feasible and satisfy all three constraints. In order to maximize our profit, we have to find a set of points that maximize this function. In order to do that, we use a method called level curves. Level curves is an easy method that we increase the objective function by a value and find until we get the point. From that point we cannot increase the objective function. Let's say we start off by a value, let's say 35,000. Let's say the objective function, this value is equal to 35,000. To solve this equation, I want to plot this on a feasible region. So I can put x1 equal to 0 and find x2, and then I can put x2 equal to 0 and find x1. If I put x1 equal to 0, I get x2 116.67, and if I put x2 equal to 0, I get 100. So I get 100 and 0, this the second point, and the first point is somewhere this area. So this function, this line shows all the values that my objective function is equal to $35,000. We call this line as a level curve, and every point on this line have the same objective value of the 35,000. Now I can increase this 35,000 to 52,000. By increasing the 35,000 to 52,000 and finding the points, we can get x1 equal to 0, x2 150. So this point, and x1 and x2, x1 is 175 and 0, so somewhere around here. And then if I connect this line, I get every point on this line will have the objective function of the 52,000. You can test it. For example, let's say I put 100 and then I can find the point on this line, and you can again plot this line. So all the points on this line they have same objective function of the 52,000. I increase this function until I get to some point that I cannot increase it furthermore. If I increase it a little bit, it would be past feasible region. It's not any feasible point. As presented in this picture, you can see that this point is an optimal point, and if I increase a little bit, if I increase this function a little bit, we are not in the feasible area anymore, and the solution we will get is non-feasible. That means that we are violating some of the constraints of the problem. So this is a optimal solution of the problem.